Welcome to ATDI. This is another webinar. This will be more like a tutorial, and we're going to talk about managing interference between 5G towers or new 5G sites and the aeronautical radar for the air traffic controller. Now that webinar is going to be detailed, and it's going to take roughly 40 to 50 minutes, maybe an hour. So first, let me introduce myself. My name is Yahya Khalid. I'm a senior spectrum engineer. I've been with the ATDI for roughly 10 years at the time of the recording. And you can see my contact details on the screen. So if you have any question, feel free to contact me. I'm based in Sydney, by the way. So the topics we're going to discuss today, first I need to give you a general overview of what I'm trying to do or how the process works. I'm going to also walk you through the project setup process, all the way from map download to 5G site importation, radar network modeling, and I'm going to shed light on the sanity checks that you need to go through, and move on to interference analysis methodology and running simulation and mitigation measures. So mitigation is about how to make sure the 5G can coexist, the 5G site can coexist around the airport. Not all 5G sites need to do coordination with the airport. So this is the model we're trying to construct, and we're going to do this together today. So the airport is in the middle of the screen here, and then you've got the radar, and we've got the 5G sites. And that first red circle is the 1.5 kilometers, and the second red circle is the 7 kilometers. So the coordination is needed up to 7 kilometers, and we're going to take the UK approach to spectrum to coordination, technical framework for the coordination process between 5G and ATC radars, as an example. So sites beyond 7 kilometers, they don't need to coordinate. Sites within 7 kilometers, they need to coordinate. This is a closer view. You see where the radar is. The radar is here, and then you've got 5G sites. And these 5G sites are randomly generated. They're not actual 5G sites. It's just for demonstration purposes. This is the model. So you're looking at the digital terrain model at 1 meter resolution. You're looking at the clutter model, and the red are the buildings. So that's the individual buildings modeled or captured in that process. Now you see here I have 1.5K and I have 7K. So 1.5K we're using specific propagation model in the simulation, and for the greater area up to 7 kilometers we're using a different propagation model, which is ITU 450. This is a 3D model, so we're going to do 3D. We're going to use 3D simulation in order to predict the signal. The signal from the 5G sites into the air traffic controller radar. So the building height is important if you want to feed this information into ITU 450. So the propagation model engine is going to make use of the 5G parameters and the radar parameters in order to, and also the digital terrain model and the building layer. You can see in red here we have the building layers, and you can see the software is capturing or calculating the reflection part of the signal and the diffracted part of the signal on the line of sight. So the tool is going to use different propagation methodologies in order to calculate the signal level at the radar. We're also going to model 5G antenna, so the smart adaptive antenna. So we're going to model the total transmission power, the antenna gain, which is the maximum antenna gain for the smart antenna, the transmission frequency and the bandwidth. We're going to model the smart antenna, the individual beams. This is beam 0, beam 1, beam 2, up to beam 7. So this antenna pattern has 8 beams. We're going to model the site as omni and also as individual sectors based on actual orientation of these sectors. So in the overview, now again here we're talking about the UK case. So in the UK, the radars are operating between 2.7 and 3.1 gigahertz, and the 5G sites could be operating beyond the 3410. Okay, so 3410 up to maybe beyond 3680. Okay, it depends. Now what we're really interested in, if the 5G transmission or assigned bandwidth is overlapping with the definition of in-band. Okay, so we have in-band requirements and we have out-of-band requirements. So as soon as the 5G bandwidth is overlapping with the in-band, then you need to do the in-band coordination. And regardless, you still need to do the out-of-band coordination because this is the noise part of the signal. So this is what we're trying to simulate. We have 5G. We have 5G somewhere in that band, okay, overlapping with that band. And then we have the radar operating on the adjacent band. So we need to check the impact of 5G into the radar. So you see here the green example, if the bandwidth of the 5G is outside the in-band limit, then no need to do coordination for in-band. You still need to do coordination for out-of-band. If you are partially overlapping like the orange case, then you need to coordinate only for that part here, for the in-band. If your bandwidth assignment is going up to 350, for example here, then you need to coordinate for that part. If your frequency assignment is all the way capturing the in-band, then you need to coordinate for that entire part here. I'm not going to talk too much about beamforming antennas, but this is how beamforming is working. Okay, so you have individual beams running like this. So the base station is alternating the beams. So what we do, instead of modeling as a single beam, we superimpose all these individual beams and we create a composite beam like that one you see on the left hand side. So we combine these individual beams to produce something which is describing the worst case scenario. So let's go straight now to the software and then start the entire process, creating a project and then importing the sites. So step number 1, you run HTC communication or HTC warfare, whatever the software you have. So when the software is running, when the software started, it will land on this landing page. Now that landing page, you could actually target a specific country. Okay, so you want to target the UK, for example. So you draw a rectangle. I want to download an airport or a map over a specific country. So you highlight the country and then you go to Map Download Manager. Now the Map Download Manager is going to list for you what maps are available from our online repository. Okay, so you see here out of the UK we have a number of airports available in 2-meter grid. Now the one I'm going to consider for this webinar is Bristol Airport. Let's see if it's here. So let's have a look again. This is Bristol. Here you go. So this is the one I want to download, the red part. So the software, the green is the area you highlighted. So any map we have in our repository, it would show up in that table. and once you click on it, it will show you where it is. Okay, what's the coverage. So you click the small icon here, download, and now you've got the second tab here. Now it's done. Now you can open the folder if you want. Show this in the Explorer. Here we go. This is the one. So I'm going to cut it, and I'm going to put it in a specific folder here called Live Project. So I'm going to paste it here, and then extract it. Extract files. Extract the files here. So it's coming with the building layer. Sorry, it's coming with the RBL, which is the building layer, the terrain, and the clutter. It's not coming with an image. So for the image, you need to use what we supply. We supply usually a BIM key. Okay, so a BIM key is something we supply to our customers. It's giving you access to online maps. So we have a building now, we have a terrain, we have a clutter, and we have an image. So let's make a project from this. So back to this one here, and you close it. Okay, you go to File, Project Manager. Okay, so this is now Project Manager. So you make a new project, and now you can simply just go here and simply just drag and drop. The software will be able to recognize every layer from its extension. So you can see here we have terrain now, we have image, we have clutter, we have buildings. Okay, so this is a fresh start. So go and save project, and then I'm going to save it in the same location. I'm going to call this Bristol. Okay, Bristol Airport 5G. So far so good. Now usually I need to have a PRM as well. So I'm going to populate that PRM later on. So now I'm just going to open the project. Here we go. So this is the airport. Okay, so let's import now the 5G sites, and let's do general setup for the project, and then we run a simulation after that. So step number one, I want to import the 5G sites. Now the 5G sites, I already have them here in a CSV format. Okay, so this is the inputs are here. Let me open it. So again, these 5G sites are not real sites. They're just randomly generated by the software. And here we have them in the CSV format. So in the CSV format, I have some site identification. Okay, we have site address. It could be actual address. We have the longitude, the latitude, antenna height, frequency, bandwidth, and a group. I mean, you don't need all this information, but as much information as you have is better. Transmitting antenna gain, receiving antenna gain, tilting, mechanical tilting, the antenna name. So here I have antenna name. There's many ways to do that. Now here, because I'm importing omni sites and directional sites, which we'll talk about it very soon. So here I'm using the beamforming. I'm using the antenna field, and I can map this into the software, and the software will automatically assign the correct antenna pattern. Okay, matching this antenna file name. So we'll talk about it soon anyway. So first step, go to File, Import, and then Stations. I'm going to import these stations from the CSV report here. So what I'll do, I will select the file first, the source file, CSV file. Second is you need to map. You need to map the site ID. So the site ID is call sign in software. It's column number 1. You go to column number 1, you put call sign. This one is address. You go to column number 2, you put address. Okay, and so on. So I already have this prepared. So I just need to load my template. You can save a template You see now we've got everything lined up. Cosine, address, longitude, latitude, antenna height, frequency, and antenna name. Antenna name is here, number 14. And the default coordinate system is 4dec, which means WGS 84 decimal degrees, because that's the one I'm using. Okay, I'm using 4dec. If you're using different one, then you need to use different code. So that's it. Now we need to import this, in fact, into a station database. Okay, you need to do this into the database. Now the database is not ready yet, it's not created yet. So which means you need to create the internal database. So I'm going to close this for now, okay, to show you the steps to create the station database. You go to database station here, in that menu, database station, or you can do it from here, database station database, okay. So either way, okay, either way. So you can do it from here, station database list, and then you can go here and say new, and then you can make a new one in your project, live project here. So I'm going to make a new folder called 5G sites for the webinar. Okay, so here we go, webinar, or let's call it live 5G sites. So this is how we create a link to a station database. It's empty for now. So now we go back to import, and then we're going to import stations. So you see, I still have everything lined up. So all I need to do now, don't import to the map, import to station database. Because the coordination process is happening between station database and the radars on the map. So I'm going to import the 5G sites to the database and import the radar sites to the map itself. So it might take a few minutes. You can see, here you go, it's done. Okay, you see, it's not just the stations are important, but also the antenna, the individual antenna radiation patterns. And let me give you a hint how this was achieved. So in fact, in the software installation folder under ATDI HTZ, under HTZ, you will see here we have a base folder, something called base. Here you go. In the base folder, we have antennas. So these are the ones I used. The BFA, which is beamforming antenna.msi, and I used the omni.plt. Okay, so this is how I managed to automate the antenna importation process, because that field is matching with the antenna name I have in my database. So let's continue. So back to the software here, and then go back to the station database, and this is the database we have. Here we go, select all. So these are the 5G sites we have. Let's double check the numbers. So how many we have here? We have 241. Total 241 sites. Right click, go to parameters to check the parameters. So I can see here we have 200 watt transmission power. Now sometimes you don't have to model it as 200 watt. You need to look at your setup. Sometimes you need to do it 100 watt or 20 watt or 40 watt, depending how much overlap you have with the in-band. So we have the antenna gain coming correctly, we have transmission frequency coming correctly, antenna height coming correctly, we have antenna pattern, actual orientation coming correctly. So all the important information are in, okay? So the importation process was successful. Now you could put this on the map. If you would like to display this, you put it on the map, okay? You put it on the map like this, close, and here we go. You can go to object properties, and then ask the tool to display cosine, display azimuth, and horizontal pattern. So now you can see the actual antenna pattern, you can see the actual orientation, and you can refer to the site or the sector by its own cosine. So you could continue set up the software. So let me now set up the radar. In fact, I'm going to set up the radar. Let's see where the radar is. I could choose really any location, but I believe the radar is here. Maybe here, maybe. Here you go. Actually, the radar here. The radar was also captured in the model. Sorry. So in the inputs here, you will notice one of the inputs is actually the radar. So the radar is already in that CSV. Here you go. So the radar is the last entry, and you can see the actual frequency here, 2900, and the actual location, and it has slightly different parameters and antenna pattern. So let me go to this radar and then maybe color it in red. So go to General tab and then change this color to red. Now the radar, we don't care about the transmission power really. Okay, you can put it anything, doesn't matter. And for the antenna gain, actually put it to 0 for the antenna gain for the radar. And frequency is 219, and you must use the actual antenna height of that radar. Okay, so these are the main parameters for the radar. It must be omni, and it must have 0 dBi gain. Okay, because the protection is already taken care of. I mean the antenna gain is already captured in the protection level, and the frequency must be in the range that we're looking at here. So the radar must be between 2700 and 3100. As long as it's in that range, it's okay. And the same, the 5G sites must be overlapping with that part. So 5G frequency can be anywhere, but the bandwidths must overlap with the in-band for this to work properly. So everything is in place now. We've got the radar in as red, and then we've got the rest of the sites. The orientation of the radar is not really relevant because it's omni anyway. It's rotational radar. All right. Now, the second step I want to do, so I've got the network in, 5G network, I've got the radar. Now I would like to make a vector layer, and I would like to continue to set up the project. So let's go to map vector layer, make a new vector file. So I'm going to put this vector file in, not here, I'm going to put it in the new project, live project. Here you go. So I'm going to give it the same name as the rest of the files. Sorry, not here. So it will be the same name as the rest of the files. It's going to be with a different extension. It's .rbl. Okay, Bristol Airport.vec. Done. So I created a blank file. Now also you could save your EWF, which is your network file. Save EWF. File, save network file. So it's good to save all these layers. Later on, Control S will just take care of everything. So this is the live project. And then here we have, this is the name convention we're using. So it's just going to be with different extension. So this is the network file. In the network file, the most important piece of information is the radar. Okay. Now the stations, the 5G stations, we don't have to worry about them if they are on the map or not, because anyway, they must be in the station database, in the internal database of the software. Now, if this menu if it is bothering you, you can go and disable it from the file preferences. Okay, here you go. You can uncheck this one. So it's all good. Now, so the sites are there, the radar is there, and that vector. So you said we're going to do the vector. So I will show you what is the idea here. I want to create circles at 1.5 kilometers and at 7 kilometers. Now 7 kilometers is the range where you need to coordinate with the radar if 5G site is being deployed within 7 kilometers of the airport. 1.5 kilometers is a sensitive area where we treat propagations as line of sight only, and we look at the reflections as well. So I'm going to use the built-in feature in the tool. You just click on the radar, you click continue, and then you go to add vector, and then you go circle. So in that circle is going to be a red circle, and I'm going to give it a thickness 3, identity number 1, and I'm going to say this is 1.5 kilometers, and give it the title 1.5 kilometer. Activate it, hit OK. Now here you go, that's your circle at 1.5 kilometers. Now make another one. You click on station again, you go to continue, you go add vector and then circle. This time you need to choose from here 7 kilometers, and here you need to choose 7 kilometers as a comment or a name. Okay, I mean, use the same color, same identity is okay. There we go. So now we've got 2 circles. Excellent. 2 circles. So now you can visually examine these sites. So you see these ones are outside the area of interest. It's not a concern to me. Okay. Now, in fact, if you want the tool to isolate stations up to 7 kilometers, you can click on the station here. Click on the radar, I mean, and then in the radar under the site, put the radius, put the extended radius. Where is it? The extended radius here. Put it to 7 kilometers. 7 step. So 7 kilometers. The advantage of the 7 kilometers now, if I click on that radar, I can tell the tool, please select for me the stations, isolate the stations, 5G stations here we're talking about, within the extended radius, which is 7 kilometers. So look what happens now. So all the sites that are outside are deactivated, okay, including the radar itself. So you might need to reactivate the radar. Activate, here you go. So I could delete the rest of the sites here, Control R. So Control R will take care of them, and then it will just deactivate them. So now I have the 5G sites that can be problematic to the radar, and I've deleted everything else. Now the next thing is I need to do some sanity checks. So sanity checks, for example, I mean, usually I'm looking at what? Looking at if the importation is done correctly, if the frequencies are correct, if the power is correct, if the antenna height is correct, if is the azimuth is correct, bandwidth, transmission gain, and so on. So it's just to do some sanity checks. And you check a couple of sites to make sure you're happy with them, to make sure the antenna is making sense to you, and so on. So this is different things, general things. Now, one thing you need to know, with the propagation model ITU 450, which is used for terrestrial coordination process, you need to make sure that the antenna heights of these sites are actually exceeding the clutter height. For example, I'm usually worried if the site is sinking under the building. That happens if the building height is above what you expect, or if the antenna height is below what is expected. Okay, sometimes the source is not very clean, so you need to be careful. Here you can switch to the building layers. So you see this is the building layer. So you can read here the building height. You can see it here under the clutter here. So you can move and then you can read. So here I can tell that the building height is, for example, 7 meters. Okay, and I can check what's the site height. The site height is 30 meters. So definitely this is okay. So you can't do this manually, of course. So there's a function in the tool to tell you which sites, which antennas are sinking under the building layer. Now you can do this very quickly in the software. You go to Object, and then you go Activate, and then you go to Isolate by Query. Okay, Isolate by Query, and then you say, all right, I want to isolate the indoor and in clutter. So indoor and in clutter means if the antenna height is inferior to the clutter height or building height. So you do this, now you see they all deactivated, which is good news. If one of them came active, then it means there's a discrepancy between the two. All right, so maybe we could take an example here, and then I can make something wrong and then see how we can fix it. So let's look at one of the sites. Let's look at this slide, for example, here. This is in the building area. So this building height is 5, okay? Let's say somebody accidentally gave us here 4 meters height, okay? 4 meters height. So you need to see if the software can pick up that mistake. So you go Object, and then you go to Activate, Isolate by Query, and then here we go, hit OK. Here we go, picked up right away. So the software noticed that this site antenna height is inferior or is less than the building height. So you need to go and fix it after that. Okay, you decided to boost it beyond the building height. Otherwise, the engine will underestimate the impact of that site. The predictions, the path loss will be more pessimistic. So I'm going to put it back to 30. Okay. So yeah, so this is how it works. Now, if you make any changes here, you need to go back to push back. You need to push back these stations to the database. Okay, so you need to push it back there, all of them. All right, done. So now I updated my model in the station database, because remember, whatever you do on the map is on the map. But if you want to make the changes in the station database, which is here, then you need to push it from the map to the database, and that's what I just did now. So to avoid, to make it simpler for me now, I'm going to just isolate that guy, isolate that radar, okay? I don't want to worry about the 5G sites on the map, because I already have them in the database. So now let's continue with the setup. So we've got most of the job done now, but I need to look after the propagation modeling. And I need to configure the software a little bit, okay? So make sure that the software is able to read the clutter correctly. That's the first thing. This is the clutter I have in the area. So the red I expect is a building. You need to read here as I move. So this guy is a building. Yes, correct. This guy is a park. Yes, correct. This guy is a road. Yes, correct. So this clutter has been manufactured, has been created from scratch to match ATDI's expectation for the clutter mapping. Otherwise, you need to change things around. Okay. So it looks like we've got the good model in place here. So this is matching this, and the clutter settings, propagation modeling, propagation model. So a propagation model, you have to use the correct one for your case. Let me see what I have here in my project files. So I'm going to use ITU for 452, I believe, 452. We have 452-16 and we have -14. Okay, now I already have a setup for the model, for the ideal model you need for this kind of work. So I'm going to load it to make it easier, and then we talk about the settings again. So I'm going to import an existing PRM file. Here we go. So this is the model I'm going to use, ITU 452-16. It has Delta Bollington's diffraction engine, and for the subpath, we're using ducting, we're using multipath reflections, okay, 3D reflections. On any terrain height above -1, so which means including the water surface, because usually water surface is 0 meters, and you could decrease that number if you want to be on the safe side. So reflections is calculated, and then this is the definition of the mapping. Not this one. Let me click on this again. Here you go. So this is you can define here the profile height estimate and then the nominal height estimate. Okay, so here you could use the advice from Ofcom. So if you find if we quickly find here the Ofcom aeronautical radar. Let me open it. I have a PDF file ready. Okay, so we're back here. So this is the file I was talking about. So what you could do here, you could just copy this information if you want to comply. Here you go. So you see here we have the sea level surface refractivity 325. So you need to go back to the software, make sure you're using 325. Okay. So sea level 325. And then the average rate refractivity 45. You've got 45 here. Okay, dry air pressure. The dry air pressure would be probably would be somewhere here. Air pressure. There we go. This is the vapor. This is the HPA. So HPA is 1013. So you can go. You see, it's 1013. Nominal path center latitude This is usually taken care of by the software, because the software is using the map. Temperature 15, you can see the temperature is defined here 15. Okay, and then you could define all the parameters, including the nominal height. So if you're using a medium resolution clutter, then you need to copy this individual information. So you've got here the nominal distance, and then you've got here the nominal height. You just need to copy across the parameters from here to here. Okay, so that's it. Now we've got a model which is compliant with the requirements. So we've got the propagation model in place now. Propagation model in place. Now we need to go and save your clutter. I mean your PRM. This is the first time we save PRM. Otherwise you lose all your settings. So I'm going to save my PRM here in the same location. All right. So I'm going to choose the same name as everyone else. Save. Awesome. So now we've got all the layers we need. Okay. So now we got all the layers we need. It's time to do interference analysis, but before that I wanted to talk about the methodology and how it works, what the software is doing exactly. So this is the slide we want to continue on. So what we are doing here, we modeled the radar, and we characterized the radar, and we modeled the 5G sites, and we used the actual orientation, we used the actual parameters, mechanical tilt 0, and smart antenna, transmission power, and so on. So what the tool is going to do, the tool is going to apply rules of physics, okay, based on ITU 456, I think, tools propagation model, or 452. So we're using 452 propagation model. So we are calculating the propagation path loss based on ITU 452. Okay, and we have the full model of the 5G sites, and we have the model and the location and the height of the radar, and the software is going to predict the impact by using these two techniques. One is it has to do with the ACS of the radar, so it will check if the 5G is enough to cause blocking or overload or saturation, corrosion. Okay, so this is referred to as a signal. This is the in-band signal. So we're going to check if the in-band signal is strong enough to drive this radar into nonlinearity. Okay, and then lose performance. So this is the in-band signal, and here we're going also to check the core channel interference. Now I know 5G and the radar are on different frequencies, so theoretically there's no core channel, right? But in fact you've got out-of-band emissions leaking from the 5G site into the adjacent band. Okay, so this is going under the spurious emissions or out-of-band emissions. So this emissions is a noise, is unintended interference, and because it has no limit in terms of spectrum, it can fall into the channel, into a side channel of the radar. So this has become a core channel problem. Okay, so this can become a problematic, especially if the site is too close. If the 5G site is too close to the radar, the out-of-band emissions can become a problem. Now usually the in-band signal you can manage, okay, to some degree by reducing spectrum or avoiding overlap and so on, but the out-of-band emissions, this is unintended, so this is hard to control. This has to do with the specifications of the 5G equipment, and because the radar is very, very sensitive, so the criteria is probably very, very tough to protect the radar from having interference. So this is just a dummy example to show you the 5G signal. The yellow here is the spectrum chart for just a dummy 5G or 4G site. So you see this part of the transmission, or the 5G transmission, is the in-band. This part of the transmission here is classified as out-of-band or adjacent channel, or we want to call it spurious, whatever. It depends how far you are from here. But the bottom line is, if this part of the 5G spectrum is overlapping with the in-band definition, okay, then you need to do in-band coordination. And if it is, and regardless, in fact, regardless, the out-of-band emissions is also can stretch to impact the radar operation band. Okay, so you have to do the noise analysis. So these two need to be modeled and characterized and also evaluated. So from Ofcom UK, you can see they have these limits in place. So they define the limit for in-band and they define the limit for band noise. Okay, so they've got these two limits, the blue and the red. So the blue is the noise, they call it the noise. So the noise, because it's the 5G noise coming into the radar, and this is called in-band, okay, because this is operating in the same band, okay, and it can drive the radar into nonlinearity or blocking, you know, to experience interference. So you can see in the specifications here, we have to go up to 7 kilometers. So any new site within 7 kilometers need to be evaluated. So these protection levels are based on the bandwidth of the interferer, which is 5G. So the software will take care of these values, and the software will calculate for you the protection level based on your input. This is just an example. We have 5G site on the far left-hand side, and you can see the emissions, how the software is predicting the emissions at different altitude. Okay, so you can see the impact of the buildings as well. So let's go back to the software now. So now that we talked about the interference, so let's do the simulation. So simulation is pretty much straightforward and automated, but you need to pay attention to the parameters, okay, to the importation of the parameters. You need to make sure you have the right model in place. Maybe before I do that, I need to explain to you here what I did. You see, I modeled every site as, in fact, as 1, 2, 3, 4 sectors. Okay, so these 3 sectors are the actual 1, 2, 3. But the first one, this one, is just the benchmark model. So I have a benchmark model which is Omni, pure Omni. It's a pure Omni, and this is really the most pessimistic case. Although I'm calling this Omni, I'm using directional gain. I'm using the full gain of the smart antenna, 25 dBi. So it is Omni, and it is. If you don't want to use the word Omni, you can say non-discriminating antenna, non-directional antenna. But their antenna actually has a maximum gain, and that makes it directional in every single direction. So this is the worst case you could imagine, because the tilt has nothing, the tilt cannot discriminate the signal. So when the advantage of this is that I can ask the software to do analysis based on this Omni and based on this sectors. Okay, so because when you want to shut down a site, you don't need to shut down the entire site. You shut down the sector which is causing a problem. Okay, we'll talk about this when we do the mitigation measures. So let's continue now. We need to run the analysis. So you go to spectrum and you go to national, regional. So you can see we have a number of coordination automation process, I2U, FCC, NTIA, okay, Europe, and here we have some countries. We have here UK. Now the one I'm interested in is this one. So software is deactivating that feature. That means I missed one step. Yes, I did. So that object here, the radar object, need to be classified, in fact, as a radar. Okay, so you need to classify it as a radar, not a normal site. So here we go. Now it's a radar. So I moved it to radar. Then go back to spectrum, and then national, and then you see it's activated. Okay, so it needs to be radar. So you click on it, and now you put the transmission bandwidth. The transmission bandwidth is 60 meg, if I remember correctly. Sorry, not 60 meg. So this is the transmission bandwidth of the 5G. It's not always 60 meg, like I said before. So you might need to talk to us first to give you the guidelines. It depends how much overlap you have in the 5G band, in the aeronautical in band. As per definition from Ofcom. So here we have the out-of-band emissions, and this is EIRP, okay, including antenna gain. So the out-of-band emissions, this is something you need to extract from your equipment, okay. So it could be neg 90, it could be neg 110, it could be something else. So this is based on equipment. If you want to use the 3GPP guidelines, then I can guarantee you all the sites will fail. So we expect the 5G equipment to exceed the 3GPP requirements. So this is done, 60 meg, you've got here neg 110, and here you need to really, here, database station, you need to go back here and select all. Don't forget this step, very important. You need to select all of them. Max distance up to 7 kilometers. So the software will ignore from the station database any so you could have the national network in that database, and still the software will ignore all the sites outside 7 kilometers radius, okay. So and the model I already see this advice here to use 452.16 with 0.1%. So go double check. Yes, it is 0.1%, so it is okay. So I'm going to use this technique. We have so many techniques here to do interference calculation. This technique, interference one at a time, so it's taking one sector at a time, okay. And I know you want to use the combined effect of multiple sectors, but I'm usually taking care of this using the benchmark model that I talked about. The Omni antenna was 25 dBi. So this is my benchmark, which will be the very worst case scenario. Okay, so you could use the combined analysis. Okay, so you could power sum for co-located stations. So you can combine all the sites falling in the same location. You can combine the powers based on antenna discrimination, of course, and then the tool will just flag the first sector that fails. Okay, as soon as it fails, we'll just report the first sector to cause the problem. So you could use this technique as well. Now, because I have the benchmark model, it's not fair to combine the benchmark model with the individual sectors. So I'm going to use this technique for now. Okay, I prefer this technique because it's giving me control. I can later on calculate if there's combined impact. So the idea is that one can start with a site model only, and then the sites that are problematic, you can upgrade them to sectors and then study the problem. So I'm gonna use this and then hit OK. So do you want to select another station? You can say no, you can say yes. But if you say yes, the software is going to select from the station database the sites that are problematic, okay? No, I don't need this step for now. I'm just going to say no. And then I'm going to see the report. This is the report. So the report is very useful. I'm going to delete this all. I'm going to go here, data. And then I'm going to go with the filter. And I'm going to sort by distance. So smallest to largest. Here you go. So knock means failed. Okay, failed for some reason. We'll talk about the reason soon. Okay, knock means failed. Okay means okay. So when you look here, this is my convention. So when I see 975, for example, this is my benchmark site. When I see 1 to 3, that means individual sectors. So this is my benchmark site model, and this is my individual sectors. So I can see how they fail. So the benchmark is failing, and the individual sectors are also failing. Okay, now I'm going to introduce here another, I can introduce an equation. Okay, so I'll talk about the equation here. Let me just copy the equation. I've got it here already. It's Excel equation. So I'm just going to copy it from one of these reports. So I've got the equation now, so I'm going to paste the equation here, in that column here, in T, okay? And the equation is simply, sorry, this is not the equation. So here we go. That's the equation, and I'm going to propagate it. Here we go, all the way down. All right, here you go. So this is a simple formula. So it says if the margin, we'll talk about each one of these. If the margin is negative, that means you failed the Ofcom requirements. Okay, for either in-band signal, this is a signal, or in-band, this is the margin for out-of-band, which is the noise. Okay, these two are critical things, critical information to look at in your analysis. So the margin tell you how much you failed or how much you passed. If it's a negative, means you failed definitely. If it's a positive, it means you passed, and tell you how far you passed. So here here is the equation. So the equation says if the margin for out-of-band emissions for the noise is less than 1, so I have 1 dB margin here, it should be less than 0, then you power off that sector. Otherwise, if the second margin, which is the in-band part, it depends how much overlap. Okay, so you can recommend 20 megahertz or 40 megahertz or 50 megahertz reduction to your transmission bandwidth. And this is something case by case. Obviously, I cannot give you a generic figure now for depending on your network, how much overlap you have in the in-band. Then you can propose a suitable shutdown or reduction of transmission bandwidth. Otherwise, it passed. Okay, so this is the formula. So let me talk about each one of these first. So here we have the radar, the impacted radar. Here we have impacted radar. The frequency. Here we have the cosine, the sector we are looking at. So this is the site, and these are the sectors. And you can see here we have address, for example. I'm using the address field to say it's a site, it's a sector. Frequency, this is the radiated power. It's also good to talk about this here. This is the threshold. So the software is calculating the threshold, protection threshold, and calculating the unwanted signal. So unwanted signal is 31.8. The protection is 1.9. So you failed miserably, really. So here you are significantly above the threshold. That's why the margin. So the margin is simply this minus this. Okay. So this is the margin. You failed by 29 dB. Very, very bad situation. And here is the threshold for the noise. You can see here threshold for the out-of-band emissions, and here how much is out-of-band emissions. So again, the margin is simply the threshold minus the unwanted signal. Okay, so simply this minus this, you get this, and then you can tell which sector. You can find the azimuth, radiated power, separation distance between the radar and the site, the status as provided by the software, and status as I would like to see it. Okay, so the recommendation is, for example, you can forget about the sites, look at the sectors. So you can see the recommendation for these two sectors is to reduce the transmission bandwidth by 20 meg. For this sector here, 9753 is to power it off. Okay, now let's visualize this on the software. So to visualize this in the software, what I usually do, I just go I remove that filter from here. Okay, you go here, you select only the ones that are 20 megs and power off. Okay, so you copy all these cosines here. Okay, these are failed for some reason, okay, or another. So they failed, but we have a mitigation. So the mitigation plan for this site, some of them is to power off completely because they failed both, for example, in-band and out-of-band. So there's no way, even if you reduce transmission bandwidth, there's still the noise is too high. Okay, now unless you can reduce the transmission power. So I'm going to copy all the sites that have problem, and I'm going to paste them maybe here in the live project, make a new notepad. For example, say these are failed, and then paste the cosines here. Okay, now that we saved the CSV file, now let's identify these failed sectors, and let's give them different color. So what you need to do here, you activate all, Control A, activate all, then you go to object, and then you go to activate, isolate stations from file list. So I'm going to navigate to this live project here where I saved the failed sites. go, field sites, hit OK. So these are the sites that failed the coordination procedure. So now you can go target them, say object, change station color right away, and then change into red. So only these that are activated are changed to red. Control A to activate all. Here we go. So now we can see clearly which sites have failed. So you see the red sectors. If you see red sectors, that means that sector has failed. Of course, you can give them different color. You can give a unique color for the sites that require power off, and for those you can also use another color for the sites that require X megahertz reduction, and so on. So here I choose just to give him red color, means that site has a problem. So look here, this is the radar site. So this site completely failed. The benchmark, which is the Omni, have failed, and individual sectors have failed. Here we have individual sectors also failed. Here we have two sectors failed. This one passed. The blue one pointing away from the radar passed. Now this guy here, you see, also same story. This one pointing away passed. This one same story. Here we have two sectors passed, and this red sector pointing to the radar failed. Okay. Now if you want to do some quick analysis, see what's happening, you could do that. Okay. You could run analysis from here to the radar, and then you can see. Now, regardless, because these sites within 1.5 kilometers, the software is using free space formula plus 6 dB margin on top of it in order to compensate for multipath and for reflections. So you see, we successfully now produced this comprehensive report. This report is extremely important. Okay, it's extremely important to understand which site failed. Now, usually after that, I also look at the combined effect of the sectors. You can combine effect using the margin here. You can calculate an effective margin or combined margin for sites that actually passed. Okay, so this is pretty much how you could go about doing interference analysis from 5G sites into the aeronautical radars operating in the what was the band, 2 point something, operating in the band 2.7 to 3.1. Okay, so this is the sort of outcome you can produce. You could produce this detailed report that has individual signals and protections, and you could make a decision after that, which one passed, which one fails, and then you can do further analysis. Okay, so I'm going to close this one. Now, if you want to consider the combined effect, you like I said before, you can still run it, but it's not fair here because you've got the Omni model. The Omni model is going to bias your results for sure. Okay, but you could do that from the menu. You have this capability here. You just need to check that box here, and then the software will take care of the combined effect of the sites. But it will only report for you the first site that become a problem. I mean, the first sector that become a problem on that site. It will not carry on the analysis for the rest. This is why I prefer to do individuals and then benchmark and then do comparison. So that's it, pretty much. This is what we wanted to talk about, and I'm pretty sure there's a lot more details we could shed light on, but unfortunately, every customer or every user has a slightly different version of the problem, so I can't use one set of parameters or talk about one case that apply to everyone else. So I prefer to keep it like this, and if you need any help, do not hesitate to get in touch with us. Thank you for your time, and we'll talk to you very soon.